today. Manuel works on many topics in the medical relativity, and we're glad to have him today talking about the use case. Thank you.
Thank you very much, and especially thanks for the invitation. This is my first time here. So I have many slides, and I'm going to focus actually. So we have a program going on for the use cases. I think mostly I'm not going to talk about the use cases itself, but how we got there. So this is some old work that we never talked much about it because we got excited about the next steps, and then we left it. But I thought it would be good to motivate and how we got here. And in case if we have enough time and we go through that old work, then we can move on to actually review spaces and evidence. If you find some slide that catches your attention, I'm going to quickly stop me and we'll see. So actually this is what we're doing with several people. So it's just giving credits to them. I want to mention as kind of really people coming from different angles. So we have people from math, applied math, we have people from modeling, we have people, physicists, on the modeling side, people from molecular relativity, people from theoretical relativity, we have some people in data analysis, some people in the interface between data analysis and source modeling. This is not a big collaboration, so this means that there are several projects going on involving a combination of all these people. So this is a list of references, then you want to go in more detail. So we'll be talking, we'll see how it goes, but maybe I'll just focus on this first part. This is essentially some work that I will start what it was, but at some point here there was a turning point for us, in the sense that we had enough evidence that the problem of modeling sources of gravitational waves could be much simpler in a dimensionality sense than, for example, years. And that prompted the whole program that we have now. But I think maybe I'll just focus on this part, and if we have time, we can move on. If not, anyway, I'll be here to know it, so we can check in more detail. And also, people, some people here have heard about this piece of work that is happening here. So I'll focus on older stuff. So just for those of you who, if any at all, who are not familiar with the issue of source modeling of gravitational waves, one issue that we have, I'm coming from the numerical relativity perspective, from a modeling perspective. So one issue is that after decades literally of work, people were finally able to model binary black hole scenarios, which you need to do in order to be able to detect the gravitational waves to do something that's called match filtering. I will not go into that, but just emphasize that it's a problem that's far from academic, and actually it is needed in order to be able to detect something. And so these solutions are now possible in an accurate way and so on. Experts here at CITA. One of the issues that these simulations are expensive. Each of them is at least a few $100,000, $60, even if you use supercomputers. That is expensive, and that's just talking about the high-end production run. There are many things that you have to do to reach that high resolution run, like convergence tests and so on. Abdul has been working a lot in order to be able to do these simulations in a systematic way, but this is an expensive problem. So why it is expensive? Well, this is what I call the curse of dimensionality, even though people in other fields will not call it that way. People in other fields would call the curse of dimensionality those problems in which you have many, many degrees of freedom, typically thousands of degrees of freedom. In the binary problem, say for black holes, we don't have that many degrees of freedom. We have, say, 8. Depends on how we count them. These are the masses of each black hole, the spin magnitudes. Here I'm just introducing notation, and the spin orientation, which is computation. Here I'm going to take normalized vectors. So this is not such a large dimensional problem, but each simulation is so expensive, and you need so many of them that it is very similar to the obstacle of the, we call it curse of dimensionality. So something was, one of the questions that we had asking ourselves 7 years ago, like 4 years ago, okay, now people can do these simulations, we can do these simulations, which ones do we actually solve for? We cannot afford to cover the whole parameter space, so we need some criteria to decide which ones to solve for. So we decided to step back and go into a simpler model of the physical system, which we could explore and see if we could find anything. And by anything, we really meant anything. So explore the parameter space and see if there are interesting regions over there, or something is happening. And actually what we meant by happening and interesting, we didn't know. We wanted to explore and see what we found. We're lucky now that we found something very neat. I think it's very good. The other motivation that we had in mind by then for doing this is that people had prediction formulas about that time for fitting formulas for the final peak velocity produced in the collision of two black holes in a non-symmetric scenario. And they're predicting very large recoil velocities. And we wanted to see, coming from some probability distribution of initial configurations of those far away from each other, you could reach some probability distribution for a given peak velocity taking place. While we were doing that, another group came up with an analysis exactly that question, which is a very similar approach to what we're doing, so we dropped it and we take a look as if we could find something interesting. So what is the idea here? We're going to look at in spiral regime to objects. Actually, it doesn't matter whether these objects are neutron stars or black holes, because there's some kind of scaling variance in general relativity, so the total mass to some extent doesn't matter much. It matters that at a different level of how many cycles you have, if you wish. But if I say we're going to focus on this spiral regime, and things there simplified analysis. So instead of looking at the Einstein equations, you can look at what is called a post-Newtonian approximation to them. Without going into the details, this post-Newtonian approximation or approximations, because it depends up to what order you go, is essentially a modification of Newton's law. You have ordinary differential equation for the position and velocity of each object, and you have relativity corrections to that. So these relativity corrections you can think of roughly as kind of a series expansion on several scales. These scales are the separation between the objects, the velocities, the individual velocities with respect to the speed of light, and the spin magnitude. How to obtain this expansion is a whole business by its own, and I'm not going to that. Just emphasize that now we are from solving a large set of partial differential equations in three-dimensional space, we are down to solving ordinary differential equations, which is trivial from a computation point of view. So within this approximation, we can afford to sample the whole eight-dimensional space of differential configurations and see what happens. Well, by then we were getting to GPU computing, so this was also a very nice scenario for us to get a little bit of an introduction to GPU computing. And this problem is ideal for such architectures because it's embarrassingly parallel and it's really embarrassing. This is a Monte Carlo simulation, multiple disconnected configurations. So this is ideal for doing large normalization. So we sample this whole initial space configurations with the statistical analysis and all the focus not on the method on how we did this and so on, but for physics of what we actually found. Because I found that to be quite neat. So as a preview of that, let me tell you the physical conclusion is that by doing all this numerical simulation and doing some statistical number crunching, we found, and I'm going to give you details of that, we found that this in principle eight-dimensional space of population essentially lives in the solutions live on at least two less dimensions to alter the surface. So effectively, what I'm saying here is that you don't have 8 degrees of freedom, but 6, if not less.
Just like to understand, so the 8 dimensions, I guess you're assuming you're on circular orbits to begin with, the large radius?
That's right. Yes, sorry for not mentioning that. So the distance between the objects doesn't matter because there is scale invariance. And we're assuming circular orbits, and the motivation for us at least, for assuming that, is that for most, not all, but for most sources for Earth-based gravitational wave detectors, the objects will circularize due to gravitational radiation before getting in frequency up. The eccentricity people have been advocating that is also important, more important than what was usually thought, but here I'm getting a conservative approach. So we did this by, we found this by doing crunching numbers, but then actually by analyzing the data a bit more, I'm going to tell you about it, we found tips of chances of doing some analytical approximation. And this is what the approximation I want to explain to you what that is. And that approximation is such that without the numerical results would have seemed ridiculous a priori, because there would have no evidence that was reasonable at all without having done numerics previously. But once we have that, we did that, we found this evidence, we did this analytical approximation. Now we simplified out instead of having lots of n to the 8 configurations, so trillions of configurations in data, we could actually have results that we can write in closed form expression, we compare to the numerics, and the reading is awesome. Go to tell you about that. All right, so I already mentioned this. It doesn't matter how it looks like. These are the form of the expressions that we're using for this particular post-returning expansion. The different colors only mean to imply the different orders that include spin interaction, spin-orbit interaction, as opposed to orbit interaction. Just if you're into this, you might notice that I'm using this only as a frequency of the system. I want to explain it because I'll come back to that later. So what we're doing is sampling this 8-dimensional space, fixing an initial frequency, a final frequency, evolving, and analyzing. And then we change this initial and final frequency and tell you what happens. So why frequency and not an initial and final time? Well, because different configurations, according to depending on the spin initial configuration, will take longer in time to reach a given final position. So using the frequency as an initial, as a starting and stopping criteria is kind of, between quotes, more gauge invariant than using a final distance. Initial common distance starting criteria.
One question I have.
Yes.
The very last equation gives you the change in the orbital plane, direction of the orbital plane. Is it obvious why the right-hand side should be normal to everything? Or does this last equation actually change the length of that?
Can you say that again?
So the left-hand side is a unit vector, and so the time derivative of the unit vector should be normal to the unit vector. Is it obvious to see that why the right-hand side of this equation should be normal to the unit vector Ln?
It's not always right. So let me skip this part actually, unless you have a specific word for any reason. Let's go to the analysis. So again, what we did is so let me go back to the questions for a second. In this equation I mentioned that there are 3 parameters, the masses and magnitudes of each spin and the spin orientations. Now it turns out that in the post-returning approximation there are kind of 2 hierarchies for these parameters. The masses and spin magnitudes are actually parameters in both the world. From a physical point of view, if you wish, what's going on is that these are kind of bare masses and bare spin magnitudes. But the point being is that they are parameters, there are no evolution equations for them. On the other hand, there are evolution equations of the spin orientations. So So these two hierarchies prompted us to do the following. For each value of individual masses and spin magnitudes, we're going to sample many different orientations of the initial spin on each object, do a statistical analysis, and repeat, not sequentially, but logically, repeat for different values of the masses and spin magnitudes. So we're going to be doing statistics on the space of initial configurations of spin orientations for each value of mass and spin magnitude. So we're decoupling these two, we have this 8-dimensional space and doing statistics on a 4-subdimensional space because of these two different hierarchies, and that turned out to be actually happy guess or choice. Okay, so let me remind you, so this is what people should tell me that, or tell you that if you want to bring up something that you think people might know or might not know, instead of preaching what it is, you should let me remind you what the principal component analysis is. It's a standard technique of a multi-dimensional statistical analysis to find essentially if you have some set of variables describing something, you want to find a smaller set that accounts for most of the variation in the data. So this is a linear technique. So you have a set of stochastic variables, and you're going to find some combinations of them, linear combinations, which are called principal components, which are going to be ranked according to how much they account for of the spread of the data around some mean value. I'm going to make this more precise for the problem that we're looking at. So the principal components with largest variances are the ones that describe most of the spread in the data. The principal components with very small variance are kind of concept quantities. I'm going to go to that point in a statistical sense. Depending on who you're talking to, people are sometimes interested in the largest component, the principal components with largest variance, because if you want to account for some phenomena. Or in our case, actually, I'm going to be focusing on the principal components with smallest variance, because we're going to see that the smallest variances are very small, and that means that from a statistical point of view, there are quantities which are essentially constant. So I'm going to focus actually on the opposite angle that most people do in this kind of analysis that we have. So again, if you have some future components, I will see that we do have some of these problems with small variance. That means that in statistical sense, these quantities are conserved, and as you might be guessing, we have quantities that are conserved to a very large, very high accuracy situation. As I mentioned, we're decoupling the space solution population to hierarchies, and the statistics, as well as component analysis, is going to be done on the space of initial configurations for the spin directions. All right, so let's go a little bit more in detail now. We want to look at the dynamics of the spins, the spin orientations. That's why there is a hat for each object, and the orbit under momentum. And whatever we look at, we want it to be invariant under change of coordinates. That's why, and there's no deeper reason, why we put the dot products between them. We can do other things. But at least these three guys are independent of the rotations of the change of the coordinates. That was the only motivation. This delta here means final minus initial state. I'm skipping part of the history here. At the beginning we did a PCA, including the initial and final states, and we found some structure that told us that we should just be looking at the differences, so I'm going to skip that part of the history. So in this principal component analysis, once you have your stochastic variables, which in our case are going to be these three delta quantities to some way, you build what is called a covariance matrix. Again, if you are puzzled, this is a completely deterministic problem, and we're doing statistics, and we're calling these stochastic variables because we want to see what is the generic behavior in a statistical sense when we sample enough initial configurations. So you build a covariance matrix. Here is going to be a 3x3 matrix where the entries are going to be the covariance between the different variables. Just to remind you, the covariance in general for two variables is the expectation value, this bracket hundreds of the product minus the product of the expectation values. The expectation values here actually should be a W integral, is an averaging over the space of initial spin orientation. That's why I have an integral of the sphere because each unit vector can be thought as a quantum sphere. So in PCA, once we have the covariance matrix for whatever you're looking at, you diagonalize it, and by definition, the eigenvectors are the principal components, and the eigenvalues are the square of the standard deviations of the distributions. So if you have a principal component with a small eigenvalue, it's a very narrow, thick distribution around the mean value. If you have a principal component with a large eigenvalue, it has a very large spread. It's a linear combination. In our physical case, it's going to be like this. This is a linear technique. These are eigenvectors. And these coefficients are going to depend on the initial masses, the initial spin magnitudes, the initial starting point, and the final starting point. In our case, frequencies. For the time being, these are going to be numbers coming from the numerical simulations. But then I'm going to tell you how we could model this in closed form of expression using the numerics to very high accuracy. So far we're going to have three of these, and in order to make kind of a logical introduction to the results, and also we did this because we wanted to touch bases with previous work by some of our colleagues, not in a statistical sense, but in our concept quantities in the post-internal equation and so on. I'm going to drop this spin term from the analysis, not from evolution equations, but from the analysis. So we still have spin interaction. So in this case, there are two principal components, which are linear combination of this dot product between the spin of each object and the orbital momentum. And here I'm going to show you a generic plot of what happens, and then I'm going to, for a particular case, and then I'm going to describe the general case and move from there. So this is a particular scatter plot where here this delta 2L and delta 1L is a shortcut for this delta S1 dot L. So this is a scatter plot, and in principle, the interesting thing here, if you have no structure, the visible numerical simulations, we have 100 simulations for this particular plot, but I'm going to show that this is generic. It's for equal masses and maximal spin magnitudes. That doesn't matter, it doesn't depend on this. It's just an example. So in principle, the points could have been anywhere on this plane. It turns out, and this is a nice thing, is that they all live in a one-dimensional subspace, which, lucky enough, is not just one-dimensional, but also is a very straight line. And this is good because if you have the strategy is telling you that all the solutions live on this subdimensional space. So it could have been that you had a subdimensional space which in this variable was very curvy. But lucky enough, and that you will not pick it with a linear technique unless you chose the right variables, but if you don't know what you're looking for, you cannot do it. And that's part of the use basis business that we might or might not talk about. How to look for this kind of structure without making guesses.
What is the physical reason behind this particular line? Is there some preserved effective spin? Or?
Yes. So let me try a short answer. For those of you who might not know, the following, and I can expand on it for that. If you look at the principal component with the smallest variance, you take that expression. As I'm going to explain later, we can get a closed form expression for that. This is something that we call instantaneous approximation. So you take that closed form expression, you turn off spin-spin interaction, evolution, and explosion of motion. You make an algebraic approximation that reduces to a concept quantity in that regime that we can perceive now. It's not the effective spin by the mole. It's not. But it's what people, it's called S naught in the most important approximation. So, I mean, actually this is the reason why we drop these spin spindles, because we let the patch cases with what they can have done. Sound good? Okay, so I'm going to next make the point that this is generic thing. This dot is for equal masses, maximal spin magnitudes. And I'm going to show you that this is generic. And then I'm going to move into how to actually and why we were prompted to try to model this analytically with success. So before getting there, let me show you probability distribution for this same configuration. This narrow line is showing the principal component with the smallest values. This brother histogram, or histogram, showing the second principal component with the largest values. Just to get an idea of how narrow this distribution is, these variables can go from -1 to 1. So this is very narrow. I'm going to quantify that in a moment. This dashed line is, I was not going to bring it up, but it's a comparison with the dense quantity. If you take a dense quantity, but you include spin-spin interaction, you do not do an additive approximation, how well is conserved is it compared to our quantity? Well, we did this for literally many initial masses and spin magnitudes in the pictures the same. I'm not sure if that's summarize that.
So, basic question. Spins aren't buoyant normal to the orbit and precisely around. And so it's a very complicated thing to map what the spins are at one particular snapshot, what they were, say, at infinity. Now, are you telling us that I can essentially say something more deterministic about how the spins are going to evolve at any future point in the between a single binder based on what they are at some initial state?
Yes. Once I am over, or once I can finish more or less with what I want to have, let me go back to that, because we look at yes, the answer is yes, but we look at quantitatively how well we can make these predictions. We can discuss it. I don't have it in the slides. It's on the paper. That's one consequence.
The comparison is what you can receive from.
Sorry, by the way, tell me if you need me to speak up, because sometimes I tend to refuse. Yeah.
So
can you speak up?
Yes. So, the quantity that you found is conserved better than what you can receive from, because you included the spin in the evolution.
Because of that, and also because we do not assume any adiabatic approximation.
So actually including all the terms help into getting the...
Sorry?
Actually including all the terms into the evolution does help in...
Yes. And actually I'll show you that we can do even better than that. So this is, I'm warming up to it.
Can look at equal mass.
And that's another point. That probably I think, no. It wasn't equal mass because I remember in the equal mass case, his quantity agrees with the degenerates and agrees with the effective spin by double. So he was considering different masses. No, I don't think maybe he was considering maybe equal spin. I think it was quite ahead. Okay, so I mentioned that these coefficients of these linear combinations of the original variables, the coefficients there depend on the spin magnitudes and the masses of each object and the initial frequency and the final frequency. So we look at the data, the numerical data. This is the next insight. We look at the numerical data and how much these coefficients here, this and this, depend on the initial and final frequency. So And you see that the coefficients change, but very weakly. So we started doing some numerical experiments, like how weakly? Okay, we start changing these initial and final configurations, and they change very weakly, so we thought, okay, so we're doing many orbits. Yeah. Many. I said, okay, let's do less and less and less and less and less orbits, and see how these coefficients change. And they change, but not much really. So that prompted us to the following thought. If we can really push this final configuration not to be thousands of orbits beyond the initial one, but really close, and this coefficient do not change, maybe we can actually push it and go to the limit in which the final state is infinitesimally away from the initial one. In that case, we thought, if it still holds, we can do what we call an instantaneous approximation now, where we can build this covariance matrix without doing any numerical evolution. We take the final state, the initial state, plus delta t, the right-hand side of the evolution equations. In that case, we will get analytical or closed form dependence of these coefficients in that approximation on the spin magnitudes and masses, as opposed to having a huge table of numbers. Next, we thought, okay, we'll build that covariance matrix. These expectation values, because equations, the positive equation are non-linear, so it be very complicated. It turns out that Chad was smart enough to actually compute these expectation values in closed form. What is helping you there is that we're assuming an uniform initial distribution of spins. So based on parity arguments, you can compute many of these things, you can cancel many of these things and compute the ones in closed form. If that had not been the case, what actually I have in mind is compute these numerically using many samples, but at least we have the dependence on the spin magnitudes and masses in closed form. So we did that. And the agreement is very good. So just for this example, I'll show you the more generic case later. These dotted points, these dots show the instantaneous approximation using the numerical data for many cycles, as opposed to the physical components just using only the numerical data. And in the other case, there are dots there that you see the difference. In other words, this instantaneous approximation works very well. And let me go back to how well in the generic case in a moment. So I told you that because of pedagogical purposes in order to touch base with what Etienne and Sim have done, we have dropped this in the analysis. Okay, now that's what we call this spin orbit case, because we do not spin. So this is the blue line, I'm going to tell you what this plot is. And then we're including next the spin terms in analysis, which is the red line, and we're going to describe this. And this non-linear means that in the PCA, we choose bilinear combination of these dot products. It turns out that these are still independent from each other, and that has to do with the fact that we're taking differences. But it's not perfect. So let me explain what this plot is. This plot is showing the smallest item value, so the variance for the best conserved principal component as a function of one of the masses. This is for maximal speeds. And the total mass is set to 1 without loss optionality because it scales up. So what I want to show is that as you go from spin orbit and include spin, you get something very conserved. And then when you look at the bilinear combinations, it gets even better. This is what prompted us, one of the things that, and you can imagine that if you look at more, if you had a better guess of which quantities to use for a principal component analysis, you will get something better and better concept. That was prompted us to later go into methods which do not require any guesses of what you're looking for. But let's stay here. You see here that there is a suspicious dip in the variance. If you look at the numerical data, this is for equal masses. So this is equal mass x, this dip. If you look at the numerical data and look at the variance here, it's 10 to minus 15, which is suspiciously enough is done position power. So we took this numerical data. We took the instantaneous approximation expression for this. We set it to the equal mass case. We plugged it back in the Poisson-Generet equations, and voila, it turned out to be an exactly conserved quantity. We went back to the people who developed these Poisson-Generet expansions, and we told them we found this exactly conserved quantity. No, people were not aware of this existence. Let me show you, for the principal component with smallest variance, a three-dimensional plot of how this smallest variance changes with the mass of one of the objects. The total mass is set to 1 without loss of functionality. One of the spin magnitudes, the other spin magnitude. Nicely enough, this is a problem which is exactly three-dimensional because we can set the total mass and we can visualize it. So this tells you in parameter space how this variance changes. We can see that the maximum, this is from numerical simulations. The maximum value is around 10 to the minus 5. If you use instantaneous approximation for this, you lose about an order of magnitude. So the smallest variance goes up to like 10 to the minus 4. So you lose precision, but you gain simplicity, because instead of having numbers, then you have closed form expression that you can get from over data. This dip here, the blue, that line is essentially the exactly conserved quantity that goes up to power. Something interesting here that you can see that the peak and the variance is not for very large mass ratios as some people thought, or our colleagues. The worst case is going to be the one where we have a large mass ratio. No, it turns out that the worst case is where the mass ratio is around 0.3. So it's not far away from the mass case.
So this plot suggests we need to do oversampling the derivation.
I have results of the new spaces for you on exactly that I was saying how I'm not sure But yeah. This matches very nicely with what we were doing for this space. So there is a whole picture. Alright, so what does this mean? That out of these quantities, there is some bilinear combination or linear, depending on how much amplitude you want. It's such that the solution lives on an anchor surface of lower dimension. I emphasize here that there is a principal component for which the largest value is 10 to the minus 5. There is a second, the next one, has values that goes up to 10 to the minus 3. So you can reduce the problem effectively not by 1 degree of freedom, but by 2. This is not an exact reduction. These are not exactly conserved quantities. And these variances are not because of numerical errors. This is a real deviation from this subdimensional space in which the solution is except the equal mass case, which is exactly conserved quantity. So these very tiny variance are not numerical errors for the solution.
Have you looked at various PNOs, stuff like 2.5 or 1?
Yeah, so I'm going to talk about that. So something that you might ask yourself is exactly this question, but in principle will change as you change the Poisson-Generet order. So I think this is the highest Poisson-Generet order, the expansion that is available, at least using these frequency values, which I thought was important. So we could have gone into lower Poisson-Generet expansion to repeatedly and see how it compares. Instead, what we did is to go to full numerical relativity and see how well this goes. So this is exactly this plot. Of course, we cannot sample the 8-dimensional space of population for the relativity, and that's the reason why we're looking at all this. So we did something simpler, but still, I think, interesting. I think you can ignore these blue and red lines and focus on the black one. What is this? Okay, first, what did we do here? Suppose that you look at this principal component in smallest variance. It's a very narrowly picked distribution, really narrowly fit. I mentioned that the variance is at most 10 to the minus 5. For something that can go between -1 and 1, so it's very narrowly fit. Therefore, you don't need many points to sample such a distribution. Okay? So what we did was to coarsen in these long post-Newtonian numerical simulations the number of initial spin permutations, repeated the principal component numerical analysis, and started coarsening to see how close we could go and still get the first digit on the coefficients in the linear combination defining the principal component, this principal component, just to the first digit. So the other principal components are going to be very odd because you need more points to get them. But we're looking at the principal component with smallest variance, I want to see how close we can go in order to get just the first digit. That number turns out to be, for the equal mass case, 20. So we did 20 numerical simulations of the full Einstein equations. Not now, of course, for many orbits, but for a few orbits. Immersion, and we go through ring down. But this analysis doesn't make any sense once you at least in its current form, we can talk about more ideas about that. It doesn't make sense once the black holes beyond the collision of the black holes because the quantities involved are individual spins and they're not well defined once we have a black hole. We had some ideas of actually going, so essentially you said that based on the initial configuration I can predict something at the very end. Actually we want to go beyond, and can you predict the state of the final black hole? But we got excited with this basically that's the question. Okay, so what I'm showing here, just let's focus on the black line. If you wish, this is using kind of something similar to what the Kenos part. Let's not go there. Let's focus on the black line. This is showing the variance of the expression from the instantaneous approximation of the principal component with lowest variance from the post-Newtonian analysis. So we have this closed form expression, and we take the expectation values using these 20 numerical simulations of the full Einstein equations. We compute the mean value, which is always 0, by the way, and the variance. Here I'm showing the variance as a function of time. You can see, so this, with the post-Newtonian dynamics, this quantity, this co-equal masses, is exactly conserved, I mentioned that. Now it's not exactly conserved, but the variance is 10 to the minus 3 for something that goes between -1 and 1. So it is, to a large degree, is conserved, especially when you got this analysis in this part of the scene, and now we're looking at the really non-linear dynamics. How far can you go? Well, at 120 here, these units, a common data horizon has to be formed. So I find this quite amazing. True that this numerical evidence only for the mass case, but here we're solving the full Einstein equations, and I'm telling you that these quantities from our previous analysis are essentially conserved to 1,000, all the way up to merger and up to the point where a black hole has been single black holes been formed. Okay, so just to recap, then we have them for questions, or we can go beyond this if you wish. So this for us was a turning point, because it told us there is obvious evidence, more than evidence I would say, but I'm finish this part, that the problem, the binary problem, is subject to what is called reduced over modeling. You can describe it by less variables than what I would do, than what you in principle need. So that motivates us to go into the whole program that we have now, which is from this point on. And the approach that we decided to take was one in which you are not so we learned here that you include more combination and so on, you were improving your accuracy or chances of producing the product. So we needed some kind of unsubtle supervised technique that will find this structure without having guesses. This is one way of approaching this to reduce spaces. And we have many, I think, interesting results here. I'm happy to give you actually a bottom line if you wish. But let me also point out that actually a little bit before we published our paper, Keith and colleagues came with very strong evidence from a different angle about the same thing, that we could dimensionally reduce the problem. Here we're looking at the dynamics of spins and so on. Keith and colleagues for the first time look at the dimensional reduction of waveforms using a single value composition. Actually, single value composition, principal component analysis, and something called proper orthogonal composition, they relate to each other. Actually, there's the same game for in different contexts. I'm not saying that we're playing the same game, but it was with more gravitational waves, we look at the spin of the map and so on. But all these pieces were getting together nicely. I think the people, I think for sure, people and colleagues and us as well, with different angles, we convince ourselves that we should push this dimensional reduction further. Let me just spend 5 minutes trying to get you excited about reduced spaces. I'm not saying that this is the only approach, but these are numbers that I like to wrap on everyone's face in a general way. Let's look for a number of templates that we need with the standard method that the LDC, the layers and correlation has been using to populate template banks. This is for initial LIGO that fixes the frequency range, non-spinning binary stars. That is the individual mass components. This is basically one of the solar masses for a given overlap error. It's what you get with reduced spaces. You get pretty much error represents an error with, well, because of what actually you're looking at, but many less. Yeah, this is 10%. And if you want to look at numbers, it's like 10 to the 14 to reach number precision compared to about 10,000 for reduced spaces. Let's look at this number 10 to the minus 5. Still the compression is like 3 orders of magnitude. Now people keep asking us, why do you want such high accuracy? I mean, LIGO is not going to detect things with a minimum match of better than 1% anyway. So there are several answers to this. One of them is that we can do it with little extra cost. Going from a 1% accuracy to round off for us is a minimal extra cost. So why not? It's like when Hayek's been asked why has been doing this spectral evolution with such high accuracy when LIGOs are going to have that kind of. Well, one of them you can do it, why not? There are practical reasons in this case, like having data parameter estimation. In my case, I have another argument why this is useful. The noise curve of the detector drifts with time. These catalogs used for mass filtering are being recomputed online as the noise of the detector drifts. In the standard approach, there's something you can do because it's very simple algorithm. Reduced spaces give you this huge compression at the cost of a very expensive parallel supercomputer offline cost. So you pay offline, but then the online representation is very compact and very powerful. Now you wouldn't be able to recompute these reduced spaces due to noise creeps online at all. We have some theoretical bounds and rigorous proof that are simple of what happens if you build a reduced spaces with a given noise curve, and then that drifts. So we took data, there's some sample data from the LSC, which was public, that's what I mean, we want to go to the LSC. Eva and Oxner guessed, like, try to duplicate those published noise clips in the noise curve and put in our error bounds on how bad will you do if you ignore those kinds of published noise clips. essentially you use a couple of orders of magnitude. Meaning that if you have a reduced basis representation which is low enough, that allows you not to have to recompute it into noise states. That's one practical reason why productivity is good. And this goes back to what we were discussing with Hannah today. Again, in these original results, we already found that you didn't need high mass ratios. But this is something we should discuss later. And this is actually something that Keith and colleagues also found, and we'll go to that. This is for, I think Keith found that this. I'm not going to go. As people probably know, we have different, I come from a modeling side, Keith's and analysis, and we're using different techniques for reduced order modeling. I'm not trying to keep on doing. But this is a question that Alan and Martin used to have. So one of the advantages and one of the angles of reduced basis compared to single value distribution is that the cost, the complexity is linear in the number of bases, vectors. For an SVD or a PCA, for that matter, it's not linear, it's product. Now, in this reduced basis business, you can make a choice, a seed. Now, intuitively, this kind of optimization, global optimization algorithms, you expect that the seed doesn't matter, unlike a local optimization method where you can get stuck in a local minimum. But some people are going to say, the reason why it's linear complexity is because you have to choose the seed. Now, if we were to optimize over all choice of seeds, so n would be n squared complexity again. That's not the case. Here what I'm showing is all the representation errors from the reduced basis, the number of reduced basis for a particular point is a range of signals, changing, taking a catalog of 1% accuracy, minimum match. Here we're showing we're running the linear reduced basis for every single possible choice of the seed. It's a 2013. Here the dotted line shows the average of the error for the simulation of other basis, and the shaded area, the maximum dispersion. So what this is telling you is that there is no need and no advantage of fine-tuning the seed. So this argument that the complexity is linear because you're not optimizing the choice of seed is not linear. Okay, so one more thing I need to get you excited. This is for the case of inspirals, and what we call SPA approximation. We will not get into that. This is a representation error. This was a reduced basis. We have three curves here. They will 2D, 3D, 4D. Blue, red, and black. This one published statement. Hope we're writing the paper for this. This 2D case is ignoring spin, so the two dimensions are the mass of each object. The 4D case is the case in which you have spins but without precession. So it's 4 dimension because you have two spin magnitudes which can go anywhere like this. And the 3 dimensional one is when both spins are aligned not only with the ordinary momentum or anti-aligned, but also aligned with respect to each other. So what is the cool thing here? As we move to 2D, to 3D, to 4D, the whole space is 8-dimensional. The number of reduced spaces that we need for any given accuracy increases slightly. From 2D to 4D, we're not going from 1700 to 1700 squared. You might imagine that the number of spaces that you need is n to the dimensional the parameter space. That's not the case. It's not even the dimension of the parameter space. It's not n to the d. So it's not 1700 squared. It's not even n times b. It's not twice. It's much less. So doing a reckless physics extrapolation, and almost we need to put some money that the 8-dimensional case you need to say, I'm overboarded. So there is precision, so reaching them, let's say 3,000 at most. That's a number that we can do in 5 years if it doesn't break down emotionally. But let me give you even a more optimistic view. What I shown you before is in spiral regime that goes between 10 hertz up to what is called the innermost circular, stable circular, the levels of the output. This is where the possible interrelation will break down for sure. But that's not where the omega relativity is doing the simulation, because we cannot do temporal problems with fast simulations. What you want to do is, say, 40, 58 cycles, 20, whatever. I'm showing here such waveforms for the mass range, non-spinning case, mass range of stellar size particles, 3 to 30 solar mass in this case. And the reason I'm showing this, I can do this because we're using this effective one-model approximation, which is a model that at least in non-spinning case captures the full measurable size. Equal 10, very well. So I'm building a reduced spaces out of this two-dimensional space using the effective one-model problem. We have to square this actually. We keep changing our notation of what we call the Tiglio error. So in order to compare with the previous one, to minimum matches, we have to square this. So why this random? We can discuss this flat random. So for an error of 10 to the minus 10, or depending on whether you want to cut here, you have about, for this two-dimensional space, we need about 100 spaces. Compared to the inspired case, that's about an order of magnitude less. So if we take our reckless, my reckless extrapolation that from 2D to 4D is basically 70s, up to 80, we can cover the whole space with random precision with 3,000 bases. What this seems to be indicating, at least in the two-dimensional case, is that you need not in the whole range of 10 hertz to this scope, but in what numerical relativity can do and will be able to do in the near future, about a factor, an order of magnitude less. So let's divide my reckless extrapolation 3,000 by 10, and that gives you 300. I'm overdoing it here, stretching our results, but without all these codes, this would mean that we can cover a whole 8-dimensional space of the relativity simulations with 300 on them. Let's add an engineering safety factor of 3, if you wish, plus 1,000. After we can still do that. Now, what I'm going through is that it has been the law that I'm finishing here, and I think still probably the law, that you cannot cover the whole 8-dimensional space of binary the whole configuration full measurability because of the cost. That's how I started my talk. I'm saying now that we are getting more and more evidence that this might be actually a manageable problem. Just to emphasize how small 300 is, if you have an 8-dimensional space, if you enter the 8, 2 to the 8 is what? Huh? Okay, so if we have an extra factor of, this is less than 3 points per dimension if you were to use a rectangular linear parameter space. It sounds impossible, right? So this is a highly, these points that you figure the method are highly unstructured. Also, you use a global spectral expansion kind of in parameter space. So what I'm trying to say is that this number, even make it 1,000, to me would have sounded ridiculous a few years ago. It's trying to cover an 8-dimensional space with 3 points per dimension. So I'll stop here. Oh, well, sorry.
Do you think that we can get such high accuracy in the EOB method, which comes from the EOB is already a few parameters calibrated to numerical relativity? There's already less complexity in the EOB than in the full numerical.
Yeah, so we're playing two games here. With the EOB people, of course, are interested in getting more numerical simulations to properly calibrate the model. In the spinless case, and also when there is a EOB model with spin and no precession, which has not been calibrated. So yes, we're working with them in order to use these calibrated or completely uncalibrated models to choose greedy points so that people can do the regular simulation, get them back to EOB to further calibrate the iterate. In doing that, we'll use some effective one-body model or chronological model beyond what is range of arbitrary, just a first guess to draw response and go back and forth. Now, I was very happy to have this dream in mind when I talked to Harald at the APS. I had this in mind of being more ambitious, and maybe we can just get rid of all these effective and not get rid of them. We might not need phenomenological models. We might be able to just model the problem purely by numerical relativity means, which for somebody like me who comes from numerical relativity, and these guys, it's kind of a principle.
But you
It's a social.
we don't use EOB to get the migration relativity waveform to do that.
Okay, I think what you're going to, it's a long discussion we have afterwards, is what happens if you don't have any guess on how to populate the time space. There's a solution to that. Fortunately, I think in our field we won't need to go that complicated. But we don't have to discuss it. This is, I mean, one of the advantages you wish of this space is you can, people use this not of in what is called parameterized problem. You want to decide on the fly which problem to solve for without knowing the solution, which that sounds kind of magic. And there is a way of doing that. It's complicated, but we can discuss it, and we don't need in our field. But
thank you. Any further questions?
Yes, I have one. So always these types of plots of error versus number of reduced basis vectors basically tell you that with, say, this particular plot, 100 basis vectors, you can represent all the waveforms. So all the waveforms are in a 100-dimensional subspace of all possible waveforms. In reality, you don't want to just be within the subspace, you want to know the parameters for each one of them. So you need to know where in this 100-dimensional subspace you are for each of the waveforms and for any parameter choice in between. Can you say something about this interpolation problem?
right. So there are two angles here. If you know, so if you start with a set of waveforms, and you can build a basis, and then you know how to recover any of the previous ones because it's part of the algorithm. Oh, this is I think what you will like. Part of the algorithm in doing this is actually offline computer representation of every number exactly. So that's so I think Harald's question is the different one. Suppose now that you want to, and you know that you can represent anything in between. So how to predict which is a question?
So basically I'm asking, if you have this reduced basis, and I give you a waveform, can you tell me what the physical waveform are?
You give me one waveform?
Yes.
Or one signal if you wish.
One signal.
But if the word physical is no. Because if you allow for arbitrary linear combinations, I mean, without extra work, which is the interpolation problem, the answer is no. Because if you allow for arbitrary linear combination of the basis, you can get whatever as physical things. So you need to be able to restrict yourself to linear combinations which correspond to the physical model. And that's if you use interpolation or this cost problem. I'll be happy to discuss what we're looking at that. But you know, it's not like a one-line punchline. Actually, it's working problem.
Well, since we're already over time, let's thank the speaker again, and if you'd like to join us for discussion,